series of presentations for these sessions, and it's my pleasure to invite to the stage Manuela Irschmuck. I hope I'm pronouncing it fairly correctly, who will tell us and give us very interesting examples on how to use space data to support the policies. Thank you. The floor is yours.
Yeah, thank you very much for the introduction. Thank you all for being here and for me to have the opportunity to talk a bit about support of current policies by space data. I want to structure my talk in three main parts. I will give a very quickly background, but it's really very quickly because Inge has laid it out already very nicely. Then I will talk about some success stories, come up with the limitations we have seen so far, and then give you a view on some perspectives. As Inge has covered that already, I don't want to talk a lot about that. I will save some time here. But just to mention, we are in this crisis, in this multiple crisis of climate and biodiversity. We are in the UN decade of ecosystem restoration, as mentioned before, and all is covered by the Sustainable Development Goals that we are all aware of. So this is the broad background, the targets, the ideas where we go on. But then when we look a bit more into the details, so where really the regulation kicks in, what has to be reported and what is the legal framework around, I want to get out like three examples. One is actually two. It's the EU Biodiversity Strategy and also the bigger one, the UN Convention, the International Convention on Biological Diversity, where we have some reporting requirements. And the second one is a very heatedly discussed issue, at least I just saw it this morning in the Austrian Broadcasting Company. It was the headline today that this European regulation on nature restoration, it is very controversially discussed, and it was supposed to be enforced already in June, but there was a tie in the voting, so now there is a new draft going on in this trilogue between the Commission, the Council and the Parliament. So we'll see what in the end this policy will look like, but there is something coming here as well. What has been ratified already this year is the EU regulation on deforestation-free commodities. So it's a regulation that whoever wants to introduce or also to export products into the European Union, certain products, so not all products, the companies have to ensure that these products did not cause deforestation and forest degradation. So this is a big step, I think, and this is something that many companies are now thinking on how to do that, and I think space data and remote sensing can play a good role here. Okay, so also mentioned already by Inge were the indicators. So of course, when you have policies in place, you need to monitor them. You need to see, are they successful? Do they, these policies have the impact that we expect? And this is usually done by indicators, and I just mentioned a couple of them here. So the forest area is a very simple indicator, for example, disturbances, degradation, area under protection in the biodiversity part. But there is also more complex indicators, of course, like conservation status. So is this ecosystem still functioning? Even if you have a forest, you can imagine, I mean, forest is not the same as forest. So that the forest can be very rich in biodiversity, it can be very structured, it can have a lot of species, or it can be a simple monocultural forest. So there's a big difference on that. And then even more other indicators on other species, like bird indices and stuff like that. So when we look at all these indicators, of course, or indices, whatever you want to call them, there is a component that space data can bring really some benefits in it. There is other indicators where we still rely very heavily on in situ data, and there's all the levels of combinations in between. So when we add up with these indicators, we have done quite some work on how to support these indicators with remote sensing data, with space data, and not only us, there has been other groups working in the same way, so I don't want you to read this in detail, of course. I just want to mention one of the publications we made out of that, because it was mentioned on Tuesday in the keynote speech that old growth forests, for example, they have a very high value, not only in terms of carbon stock, but also in terms of biodiversity. And so if you want to protect these forests, you need to know where they are. And so if you want to do that on a large area, remote sensing is one source of information that is useful. I think this is something that we all know. So, and when we talk about indicators on the policy level, this is maybe not so much known, because so far these indicators have been generated by in situ measurements, by field visits, and sometimes they take 4 years, 5 years, 6 years to cover an area, and then when you get the data, it's already outdated. So, and you have only sample plots. So this is the things that remote sensing can really give a benefit in this wall-to-wall mapping, no leakages, quicker updates than these very cumbersome, long-lasting field measurements. Of course, we should also consider that usually the costs are lower, not always, and then transparent. The products are transparent and reproducible. They are, not always. That's why there is a question mark. I'll come back on this later. Now I give you some examples. I need to speed up a little bit. One thing is we have already seen on disturbances something. So we have been doing disturbance mapping in the frame of this GTIF for Austria. Maybe you have seen the presentation the other day. We have also done that for Germany in the FNews project. And this is like disturbance mapping in near real time or close to near real time. And one thing which is very interesting with this Kalman filter that we use is that we take into account different phenologies. So we don't have one model for all the years, but with each observation that we get in, the Kalman filter adapts to the situation. So if we have a late spring, also our curve looks different. And so that helps us, of course, in better change detection on the time series. But there's also another nice thing about it. It's that with this model, we can actually predict, we can pick any time in this yearly cycle and make an image as it would be expected. So this is here the top row. This is the actual Sentinel-2 images. And you can see still there are some no data areas, there are some clouds, there is some haze maybe. And when we use the model to predict the image for this exact time, we get really clear and images that are wall-to-wall. We have no gaps. And then this is something very useful for all the further up work. Another example that I want to show, and that was also mentioned on the keynote on Tuesday, that we combined JEDI LiDAR data with Sentinel-1 and 2 to get a wall-to-wall. In this case, not height, as it was mentioned before, but vertical structure. So we look not only at the canopy, but we look also a bit into the canopy. So we see how the LiDAR points are distributed in height, and we can assess then, or this is also a kind of an indicator for biodiversity, but also for carbon. I'm coming to the EUDR. This is something where I cannot present you any results yet because the project just started. So the idea is that we track back coffee, cocoa, chocolate to the original area. And then the satellite data comes in and we can see from the time series analysis whether this area has experienced deforestation in the past years, or also of course we want to take a buffer because sometimes there are also leakages here, so we can say, okay, this part is good, or here is a problem. And then we also expect some uncertainties there, especially with sub-canopy crops like cocoa, and that's why we have in this project also a component on citizen science and crowdsourcing, where we hope that this will help with the data generation. Okay, this example is just that we're not only doing forest, it's also on grassland, so we do mowing events also from the same time series as I said before, which are also important for biodiversity issues. Okay, I'm coming to the limitations. I need to speed up a little bit. First limitation that we have seen in our data, but we have also seen with the users, is that sometimes the thematic detail is not good enough for what we need in the policies. So just a quote we had last week from an Austrian agricultural expert who said that the resolution of Sentinel-2 data is not good enough for our narrow fields. It's one of the limitations. Then, as already mentioned by Inge, this is often a big gap between the policymakers and the scientists, and they're not speaking the same language. There is often a misunderstanding, or there is also and I want to mention that sometimes if the information that is demanded by the policymakers also give a boost to the scientific community to get better, to make this happen, to make it work. So it's kind of a gap, a limitation, but on the other hand, it's also a chance. There are some missing links between technologies. I won't go into detail on that. And fourth is the limited access to data, and especially in situ data that I want to mention because of remote sensing data.
Sorry.
Yeah, sure. Okay, I'm already at perspective, so close. One perspective that we could use, and we have seen that in presentations yesterday, for example, super resolution to get better data, hotspot mapping. I saw a poster out there that you combine different satellite data sets to improve the thematical detail that we want. The second thing I want to mention is that I think we have to improve our deep learning AI parameters to get to some physical trustworthy AI and results. And trust is a very, very big thing that we should take into account. So I heard this black box issue. We should, if we don't understand anything, it's hard to trust. So also the threat of fake satellite images is an issue that we should think about. About these gaps, I think there is a very good, there are some policy formulations, policy briefs now that work really well, so way to go on this front. And then this in situ data, I think there are also some very, very good examples. I'm not going into detail, my time's up, but this is challenging, I know, but it's urgently needed. So just very quickly, take-home messages. We have these current policies. They are very good. Space data can play an important role. The challenges are there, but I think we are all in a good way to overcome these challenges. And sorry for being late. Thank you for your attention.
Thank you, Manuela. Thank you, Manuela, and sorry for rushing you, but we want to make sure that all presenters have enough time also to receive questions. So now we are a little bit tight on time, but if there is one burning, quick question, we are happy to take it. If not, then I would encourage you to really network then later on during the coffee break and to continue this conversation. Thank you again, Manuela.
Thank you.
Okay, so it's time for our second presentation by Raphaël D'Entremont from the Joint Research Center of the European Commission. We will slightly move topic, so from forestry to agriculture. So, Raphaël, the floor is yours.
Okay, good morning, everyone. So I'm not thinking we're changing so much topic because, as was said this morning, basically, agriculture and forestry are more and more close, especially with agroforestry. So I will try to bring you in this presentation to some of the work we've been doing, where we've been mapping at continental scale agriculture in Europe, and also some example of real pragmatic case and scientific case that we are converting into indicator for policy making. So this is the work that is being done with a full team. You have the name here. The context, I mean, I'm glad for the previous speaker because there was some context already set. But something that is really important is to know that the 38% of the EU is farmed, which is quite huge, and it's also responsible of a lot of impact on environment. And for climate mitigation and greenhouse gases, it's account for about 10%. So there are different policies. One of the key is the Common Agricultural Policy, but also, as it was mentioned before, there are policies in the discussion, such as the Nature Restoration Law. So all the development we are doing now will be really useful in the future, and the different policies that are being planned. So this conference is about big data from space, but I will start by presenting you a data set that is from ground, and then we will go to space and then back to ground. We were saying that in situ data are key. We have in the European Union a survey called LUCAS. Maybe you've heard about this. It's quite more than 15 years that it's running, every 3 years, more or less. And you have 1 point every 2 kilometers in Europe, and we send surveyors on the field to collect in situ information about land use, land cover, agricultural practices. And this data set is really valuable for a lot of application, but it was really designed for statistics to compute land cover and land use change, basically. Here I want to highlight this data set because we have now 1.7 million points that were collected, and this is available for any work. The problem of this data set, as I mentioned, it was designed for statistics and not really tailored for Earth observation. So we've tried to find a workaround on this by initiating a new module in 2018 called the Lucas Copernicus module, for which, instead of collecting a very narrow fraction of 1.5 meters around the very tiny points, we collect an area along with land use and land cover for different classes. So in 2018, we did 60,000 sample, and in 22, 150,000 with a simplified protocol, 82 land cover classes, 40 land use classes. And the data set is really useful because you can use it for training and calibration any Earth observation products. So I will show you some example. One of it, this is the data set that was just released. So, I mean, unfortunately, you don't see so well, but you can look on Google. But you can download the data set if you want. So you have a very detailed depiction of the land cover and land use in Europe. And using this data, basically, was one of our proof of concept that we did several years ago to map the crops at EU scale. So using this Lucas data as training data, we've used Sentinel-1 data at the continental scale to train a classifier to map the specific crops. Well, you can see here the backscattering of EV and VH for the different crops. So you have, for most of the crop, at least if they have phenological differences, you can spot quite easily with the time series the difference. So the result was a map, a nice map of a 10-meter resolution of all the parcels in Europe. So this map is available and you can use it. And basically, the next part of my talk, we will discuss how we are updating this map with the 22 version and how we can use such a map to really derive indicator for our colleagues in Brussels. So, of course, this map were validated. The difference between what we've done in 2018 and 22 is, of course, the data set used for training, so the different Lucas survey. But also in 22, we've used Sentinel-1, Sentinel-2, and land surface temperature. The map of 22 is also was just available. Babak is in the room, which is the lead author on this work. That it's a collaboration also with the Boku University, so you can download the map if you want. And what is interesting also in this exercise is that we've used the model trained over EU27 to run it in Ukraine because we needed to have a really timely information of the food production in Ukraine. And we're showing that it's working quite well also. So there is a manuscript in the making, but the product anyway, you can download them already on the GRC facilities. Well, it's nice to do cool maps, but it's not information, it's just the data. Now we'll show you several examples on how we can use really these maps to convert them into information that could be used for policymakers. One of these examples is really about the CAP, and especially in the Common Agricultural Policy, we have different indicators. One is about resilience, the impact on resilience on farming system. And for this, we had a request from the colleagues in DG Agri to know if we could do something with remote sensing to measure the crop diversity at a different scale in Europe. So this is a work done with the colleagues where we've been looking at different scale at channel diversity of crops, so ranging really from fine scale such as 1 kilometer to 100 kilometer, and also different administrative aggregation level. And we try to link that with the intervention logic of the Common Agricultural Policy. So the paper was just published this night in archive, so if you want to fetch it, it's the preprint already. What is interesting to what we saw there is that there is a really contrasted result in the EU, of course, linked to the landscape of the different countries. But if you look at the correlation of this crop diversity with farm size, that's what we did, you can really group the different countries and try to say something about the resilience of the system. So it's just to show you an example. Another example, it's a project for which we're using such a high-resolution crop type map to derive new pesticide indicators. So it could be quite different, but pesticide data is really tricky to get. And most of the time, what we use at EU level is we use indicator, a harmonized risk indicator, which is based on the sales. So we kind of report the sales at member state level, but so it's very coarse in terms of spatial definition. And here, what we are doing is that we're using high-resolution crop map to disaggregate the sales to a finer scale, and then we link that with population data to look at the potential exposure of residents. So you need pesticide data, of course, for this. You need agricultural data sets, such as the crop maps or the farm declaration. And then you need population data. And then you can really try to do basic GIS analysis in a way to look at the range at different buffer area. For example, here you see the crop map with 10-meter buffer. And you can compute for each of the region, that's the little map you see here, what could be the potential exposure of the residents to a given active substances. Another example for which we've used such a type of map was more for biodiversity monitoring. So the previous example basically was linked more to DG Santé, which is in charge of the new sustainable use of pesticide directive. And here, basically, it's a work that we done in collaboration with the DG Environment. So it's really exploratory, but we use such a crop map as a proxy for agriculture intensification, in particular the maize share that you find in Europe. And then we look at another big data source that some of you probably are aware, GBIF, which is a global occurrence of species. So you have, you can download all the data, it's open. So you have a lot of crowdsourced data there, but every point is a given species, and we look at specific botanical species that are potential indicator of agriculture intensification. And we found a correlation between the species richness of two different group of species and the maize share. So it's quite interesting. It's still on the working, but it's pretty interesting. And a last example, it's for ecosystem accounting. Some of you are maybe familiar with this field, I would say. There we've converted, if you want, this type of high-resolution mapping with, like in this example, we're mapping the potential pollination of the crops, which is very important for pollinators through time also, because you need to have food for bees and the different pollinators. And we're now working on this to make sure that such data set could be used in the future there. So the conclusion and perspective, I want to stress first the importance of the crop maps. I mean, having maps, it's something, but turning it into information that is really used for policy, it's something else. And so, but you need first to solve the first problem. So I'm happy that this is moving forward. And also, there will be a Copernicus high-resolution layer called VLCC for vegetation land component that will provide annual crop map like this, but it will be available mid of next year only. So all the development we do here, we expect that we can scale them further also. I think something that is also important is that European data are a key, so we need to have a good, of course, satellite data, in situ data, but also good infrastructure and cloud computing facility. I mean, this was discussed already a lot during here, but of course we would like to do that with the best and open computing facility. So thank you for your attention, and any question, welcome, or you can always contact me or the colleagues.
Thank you, Raphael. And we have time for one question from the audience. If there are no questions, actually... there, sorry. You were in the corner.
Yes, thank you very much for interesting talk. I could see that you mentioned that you were using Sentinel-1, Sentinel-2, and land surface temperature data for classification. So my question is, why would you need land surface temperature to improve the crop classification?
Yeah, it's a good question, but the thing is that there is some paper showing that if you use thermal time, or you can basically take into account the time accumulated to the crops, you can have more generic classifier that should be agnostic to different seasons. So far, this is still under scrutiny for this specifically, but I'm taking this opportunity to, I mean, probably you are aware that there is the LSTM mission, which is the land surface temperature mission, which is not flying yet, but it's a candidate mission for a future Sentinel. And that should provide a high-resolution land surface temperature that would improve potentially the depiction of the agriculture field. So for crop type, it's very important, but also for evapotranspiration, for modeling the need of the water of the crops, and this would be very important.
Okay. Thank you very much. And actually, if there is time, I have a very quick question on the use of this detailed map, because you spoke about policy applications and the fact that you're working with DG Environment, DG Sante, et cetera, but is this map also integrated somehow in the CAPRI modeling system, which is the economic core model that BG Agri uses?
Yeah, for sure. So the CAPRI person are in the same corridor, so we discuss. So CAPRI, they use a lot of data to model the CAP and the future of the CAP, basically. And yeah, they use any data available. But you know, when you produce such type of map, the first question is, oh, it's nice, and can I get the last 5 years? And then you say, okay. Then you need basically to have a time series, consistency. So what we're trying to do here is we try to bridge, really, that's our role as a GRC in the Commission, the science or the application to the policymaker, to show them the potential of such technology. And then, I mean, if it's really meaningful, we're funding it like we do with the Copernicus program to have such a type of indicator. Thank you.
Thank you. Okay, so now I invite, no, I see another person approaching the stage, not Sergio. Okay. Then Paola Samino, right? Perfect. So from the European Union Satellite Center, she will present geospatial intelligence services. The floor is yours. Thank you.
Thank you very much. I hope that you can hear me. Well, I'm Paula, and I'm presenting you today which are the most recent activities that we are performing to improve our geospatial intelligence services. And for that, I want to start with a very brief introduction of what we do, because I think that you might have seen us in the common space where we have a booth with ESA and GRC. We are an EU agency. We are not that big. We are like 150 people, and we work in supporting the decision-making and actions of the European Union in what respect the common foreign and security policy. And we do this support by providing geospatial intelligence services, so basically using satellite data. So continuing with that, we are like a GEOINT service provider, so we are an operational agency. We actually produce geospatial intelligence and image intelligence reports and products, and we provide them to the European Union and member states. You have here a couple of examples. So for instance, one of the typical projects that we do is some reference product to support evacuation plans. Also, you have like simulation to see what will happen if there is a dam failure, and this example is in Mosul, in Iraq. And on top of that, this is one service that we provide, but we also are the entrusted entity from the Commission to provide the Copernicus service in support to the external action. Well, now it's called External Action and Security Service. Oh, I think I mixed the word, but it's the same words in different order. So we also provide this to accredited users of the services. And on top of this, we support Frontex service in border surveillance by doing the geospatial analysis. So you can imagine that we have, like, as I said before, like 150 people, and more or less more than half of these people are working in the daily production of reports. So we are continuously working with very high resolution images. And on top of this, we have a capability development division that is like very dynamic and has a very strong focus on developing new solutions, because as we have to focus on the operational task, we have to work in parallel in activities that are really continuously improving the capacities that we have. So we have like a training services for member states and European Union agencies. We also cooperate with relevant entities like UN, with the GEO, the Group on Earth Observation, ESA, EDA, the European Defence Agency, Frontex, so all this in this ecosystem. And we perform research and innovation action that mainly we do through projects. So what are the main challenges that we are facing today? Because you can imagine that in security, it might seem that we are always looking at the same, but it's not the case. So you can feel in the last years that, unfortunately, the security ecosystem is continuously changing. We have new challenges to face. We have new situations to observe. And on top of that, we have like the global issues like climate change and things like that that might be deriving in security-related issues. So this is the most clear example of complex scenarios, because you can imagine that, I don't know, you have climate change, the increased temperature along the years is producing that there is like a scarce basic resources, and these resources might derive in conflicts. So these kind of situations are the ones that we are now requested to analyze. And this is not something easy that we can do with a couple of very high resolution images. We have to introduce here big data from space. So fortunately, we have also this explosion of data in space. So we have, apart from Copernicus, which is providing regularly data, we have also new constellation. We have some initiatives like high altitude platforms that are now, seems that are like evolving, UAVs, things like that. So this is new acquisition system that we have to study and take on board. And on top of that, we have new data like thermal, infrared sensors, hyperspectral, radio frequency signals that can provide that with some intelligence from space also. So all this data, we have to put them together. On top of that, the IT technologies are evolving. You have also artificial intelligence that is evolving and is continuously doing, and we have to also take on board this. And we are at the same time requested by users to have like clear information, simple interfaces, and information quick and fast everywhere. So this is where like interfaces and communication technologies are inserting. So these are the kind of activities, the challenges that we are facing in our, let's say, projects. And now I'm going to show you some examples of what we are doing in order to support the uptake of big data and technologies, and working towards, as, let's say, single point interface for users. So the first example are the bootstrapping services. I don't know if some of you were in the first day here in the tutorial from AI for Copernicus project, but this is a project that is doing like some of these bootstrapping services. So the idea is to ease the computational load when we have a lot of images to observe or to analyze. So basically we bridge the gap between the artificial intelligence algorithms and Earth observation raw data. So this is an example, for instance, which is an amplitude change detection with Sentinel-1. So we do it as a Dockerized application to process a pair of images and provide directly an image that can be analyzed. So it's analysis-ready data. Then a second example of technology we are working in are artificial intelligence algorithms. And we are now like focusing on two things. The first one is like a super resolution to see how images that have not very high resolution can be, let's say, manipulated with artificial intelligence and provide more resolution to assess, let's say, key information. And the second thing is what everyone is imagining, that is automatically detecting and characterizing objects. So here you have an example in the maritime domain that is from Promenade project, in which the project generated more than 12 different services for maritime awareness. Some of them were using Earth observation data, some others only AIS data. And in this example, a specific example, you can see like how checking the route or analyzing the routes of many ships, you could be able to detect trends and detect anomalies. So if you detect an anomaly, you can say, okay, this ship is not doing what it's supposed to do, and maybe it's one that we have to analyze and see what is happening. The third example, and is a very challenging example, is the data fusion one. So as I said at the beginning, there are a lot of data sources that we have to integrate, and integrate in a coherence or, let's say, logical way. So we cannot integrate data and just put it like that. We need to understand the correlation between the different data sources. And in some cases, it might happen that they don't have like anything like that can be extracted from them, but in some others they can. So this example here, for instance, is on climate security. This is from the Global Earth Monitor project. And in this project, we use ACLED data, so it's a database from conflicts. And we try to map the conflict and group the conflict to see if they could be linked to some climate change variables. So this is a very initial pilot. We were not able, let's say, to derive a model that is operational, but it's a pilot that is giving us an idea on how to build on in future projects. So basically, we can see here, and you saw, I think, in the animation, how you can cluster the different conflicts depending on the origin. And you can see also the areas with more conflicts, and then you can drill down and check what is happening with Earth observation. I think I have to speed up a bit. And the fourth example of things that we are doing is the development of a specific dashboard for risk management, because at the end, users are changing the way they access the information. So we still provide like GEOINT report, which are documents like can be one picture, or it can be a report with 200 pages that they have to analyze. These are different products that we provide, but they also need to really assess risk. So this is one of the examples that was in shape developed with MEO. And we were like trying to create a dashboard in which the risk of flooding is automatically, let's say, or not automatically, but is triggered. So you can really go to the dashboard and see what is the risk level and take your decisions. And then the last thing that we are working in, as I said in the beginning, is the way we are like working with users and also how they are accessing our resources and our services. So the idea of this solution that we call GeoDump is the GeoDump platform, that is the geospatial management, data management platform, is to have a single entry point to all the services that we are developing. So we can foster, let's say, joint communication between users and stakeholders. And we can at the same time provide results or access to results to users. So this platform has also a dashboard, and you can download data, you can launch pipelines, you can also go to thematic applications. So all the results that we do, we try to integrate it in this platform. And so the conclusion that we extract from this presentation, what we want to, let's say, communicate to you, is that at the end, the needs of our users, and I think this is not only in our domain, it's in many domains, are continuously changing. So we have to really adapt to what is the real demand of users working in policy making, decision making, and so on. And for that, we need to really communicate continuously with them. We need to provide them information that is understandable and actionable for them. And we need, let's say, to assess which data sources are reliable, how we make a combination that is also trustable, and how to provide the information to them. And for this, the ICT technologies are key. So we have to continuously working on that, and we cannot stop like saying, okay, we did this and this is all. So we have to continue working on that. And well, this is all from my side. I hope you. Thank you.
Okay, so we are ready for a couple of questions from the audience.
Yeah, good morning. Thanks for a very interesting talk, Joachim Saalmüller from EUMETSAT. I wondered how far you have dived into predictive services.
Not that far, let's say. We are working, as I showed you in the Promenade project, we were working on maritime surveillance. You can predict this because it's, let's say, for our interest, it's easy to say what we want to predict. And in this respect, we were able to apply artificial intelligence to AIS data and data trajectory. We are now working in a couple of projects like, that are starting, so we don't want to say anything, but it's to assess the risk of cascading risk, what is called. So basically how to predict what is happening, if something happens, how this affects, for instance, critical infrastructure. So this is one of the prediction, let's say, models that we are working in. And we are also working in another one that is supporting SDGs from UN, and we also are working in building on the climate security pilot. We want to see how we could predict something. But answering to your question, we are not delivering anything right now operational that is prediction. So we are very focused on the information right now.
Thank you for this. Thank you for this very interesting talk. I was wondering, are you also that wasn't clear to me. How is the mode of operation? So are you developing those methods by yourselves, or are you having cooperations with industry or with universities and science?
We have cooperation mainly. Okay, we have a capacity internal, so we have our colleagues in the unit are doing some, like for instance, the bootstrapping services are like basic processing, but when we go to something bigger, we are always counting on cooperation to access new data, to develop new algorithms, and so on. So we have a strong focus on cooperation, and we do it mainly through European projects.
Okay, thanks.
Okay, so thank you again, Paula.
Thank you.
All right, so I'm inviting to the stage our last speaker for this morning, Jesus Peña Izquierdo, will present us the AI for droughts. So, Jesus, floor is yours.
Thank you. Good morning, everyone. Thank you for being here. What I'm going to present now is a project, AI for Drought, funded by ISA. It's a much more specific topic than what has been presented before. The aim of this project is to improve our capabilities of predicting drought at seasonal timescales in Europe. And this is a project with a consortium between Lobelia, is the company I work for, based in Barcelona, the Barcelona Supercomputing Center, and Eurecat, the technological center of Catalonia. So why droughts? Droughts, as you know, is one of the most detrimental climate hazards. And it is because it impacts a broad list of sectors like energy, environmental, health, and so on. And it's also linked to other very important hazards like heat waves and wildfires. And this relation is very intimate and complex. And this is why it's very relevant to study droughts and also why it's so complex. These hazards are also expected to increase under global warming, obviously. But however, there is always hope for improvement. And if we see the trend of the area burning in the Mediterranean sector in Europe during the last decades, we can see a clear negative trend. And this is mainly explained because of effective management protocols and early warning systems. We can see also that there is a large interannual variability that also explains why we have seen this summer these crazy wildfires in Greece. But the idea is that while we are doing great, we still need, obviously, effective tools. No? And here is where seasonal predictions is the tool to go for drought management. And a typical question is, how is possible that we can have seasonal predictions if we are not able to predict the weather in the next weeks? Well, this is because seasonal predictions are not meant to provide the weather in the next month, but on the contrary, is to provide what would be the average conditions of the next month or the next season. So if the summer would be above or below normal, it would be drier or wetter than normal. And this is possible because their system has some slowly varying variables that you can see below. The atmosphere typically provides predictability at short time scales, like below a week, but beyond a week, it is land conditions, typically soil moisture, what provides useful predictability signal, but mostly a local scale. If we go beyond 30 days, now is the ocean, mainly with sea surface temperature, which provides important information for predictability at seasonal time scales, and especially at global scale. No? So we have these two scales, like land information for local scale and sea conditions for global scale. So if we look at the large-scale predictors for Europe, typically these are the two mostly used. We have El Niño, that, as you know, is a climate motor variability in the Pacific, but it has a global impact. But you can see in this map that the impact it has in Europe is quite limited, very weak, so it cannot provide very useful predictability. And then we have the North Atlantic Oscillation that is actually the main motor variability of weather patterns in Europe. But the predictability of the now in summer is very weak and is very difficult. Then we are struggling, how can we provide large-scale information for Europe for the summer? So we need to find additional sources of predictability. And additionally, we have these local scale predictors that mainly are related with soil conditions, and specifically soil moisture. So we have these complex feedbacks. When we have soil, dried soil, the amount of evaporation would be limited, and this would impact the amount of warming in there. So if we have more evaporation, part of the energy would be invested in evaporation, but if we don't have moisture, then all this energy would make temperatures increase, and this is a feedback because with higher temperatures we will have more desiccation, less evaporation, and so on. And on the contrary, we can also increase precipitation with higher evaporation in wet soils. So this is a typical land atmosphere feedback scheme that in reality is quite complex and is not well captured in climate simulation. There's a lot of literature about this, trying to replicate extremes, for example, the historical 2003 summer heat wave that mostly impacted France. And it's not possible to replicate these extremes without the soil moisture information. And this is why soil moisture, that is a variable observed and provided by satellites, is a key variable in this matter. So what is the current skill, predictive skill of state-of-the-art models? Here we see the System 5 from the ECMWF seasonal prediction system. The blue colors means that the prediction is worse than using the climatology, so than using the average conditions as prediction. And only in red we can see what areas this model provide better prediction than using just the climatological mean. So you see that most of Europe is in blue, and there are some regions with very low skill. So we really need to improve this, and what we propose is use a data-driven approach, machine learning based, to try to extract as much as possible large-scale drivers that are not, for whatever reason, captured by climate models because of the complexity, and also includes in a more direct way the information from soil moisture and land conditions. The main limitation of this approach is that since we are in seasonal timescales, let's say that 1 year is one sample. So if we want to use observations, we are going to have just tens of samples, tens of years, because there's no more observational records. But if we want to really capture these complex feedbacks, we really need complex models, what means that we need much more data. So this is the approach that we propose in a very schematic way. So on left, we have the predictors. We want to add the large-scale predictors, as we have commented, typically sea surface temperature, geopotential height for North Atlantic Oscillation, and so on. Also, we will include a dynamical prediction for the A7WF model. So this is why it's an hybrid model, because combine statistical with physical models, and also the local predictors. And the idea is to increase the number of samples. We are going to rely on climate simulations. Climate simulations are clearly idealized realities, so they are not perfect, but they are physically consistent, so it has been proved already that for seasonal timescales, training a model with climate simulation provide additional information, and it has been already exceed the skill of dynamical models in certain regions of the world. So this is a fair solution to the problem we were raising before. But then for satellite, for local conditions, since we are looking at local, we can neglect kind of the spatial coherence, and we can use a pixel-based model. So this means that we will have sorry, I just see the time. We will have samples from each pixel, and also from the 20 years training period that we have. So if we go quickly to the larger scale model, I'm not going to explain in detail this model, but we have tried different models, and it's been a challenge actually to provide some skill, but this is the one that is providing more skillful results right now. It's just a generative model that tried to train the model. The weights of the model are not meant to provide a deterministic solution, but more to capture the statistical the probability distribution of each of the models. So in this case, we are using above 150 climate simulations with 150 years, so we have 20,000, more than 20,000 years. And the idea, again, is to capture what is the probability distribution of these models. Typically, the inputs that we use is sea surface temperature and geopotential height. And these are some very preliminary results. We have for the whole globe. These are two metrics, and you see that most of the globe have significant skill, especially in those regions in the tropics that we know that should have higher predictability, and this is a good validation for us. And then we can look at Europe, and as expected, the skill is much lower, but still, from a purely data-driven model, we are getting some interesting results already. However, if we go for the predictability of precipitation, we see that the skill is much worse. We still capture some predictability in the tropics, but you can see that in Europe, the skill is very limited. So we really need to push this much further. On the other side, the local scale model, that is the one that incorporates the large scale prediction from this previous model and the dynamical and local conditions. I'm going to just explain a quick example of the different...
In 1 minute, please.
Okay. So basically, we have this inputs from the large scale, from the dynamical prediction, and from the local conditions. We train, in this case, a much simpler model, a machine learning model, typically a neural network, to, in this case, predict anomalies in soil moisture. And just to show how important local conditions are and how this simple model is able to capture this feedback, we are going to review quickly these 4 experiments with different inputs. The first one with only local conditions plus the dynamical model, only with the large scale from the future. So we are doing trick and assuming that we have the perfect prediction for the large scale. And then a final experiment that has the perfect prediction from the large scale plus the local conditions. Maybe I'm going to quickly, so this is for the first case. We see that we get a similar result than persistent, that is the benchmark we have used. If we add system 5, the dynamical model, we get a bit of an improvement. If we only use the perfect conditions, we see that we don't beat the prediction from the local plus the dynamical model. So only even with perfect large-scale conditions, we are not, in other way, the local conditions are more important even than having just the large scale. And finally, if we suppose that we have the perfect large-scale condition plus local information, we have already a skillful prediction. So quickly, some of the general conclusions. Under the increasing global warming and increased probability of occurrence of hot and dry extremes, we really need skillful seasonal predictions. However, as we have seen, they are very hard, especially for the stratotropics. But satellite observation, especially soil moisture, are crucial for describing some of the processes that explain the amplification of extremes, what implies that a data-driven approach can be a very promising solution. Thank you.
We're running out of time, but happy to take a burning question from the audience, if any. Otherwise, I've been seeing people fleeing to the coffee break, so I suggest that you contact all our speakers outside. Thank you for staying with us.